嗯，想看吗？因为不 interesting，所以没有给我看，没有什么好很好，也没有什么很坏，这样想看，没有什么，嗯，没有其他课什么有趣，就大家是来读书，要看的是可以的，没有，我觉得没有什么好玩的，哎，没有什么好玩，因为大家都来读书，然后把自己的喜欢的大家有，对啊，好像来看我表演这样。虽然有人在那个三楼读，刚才提出的人比较多吧，然后专门都会讨论到，所以他们那个好好觉得在是的时候是，他也是圣罪，也是什么圣罪的，什么叫圣罪？就是做完的时候，你做完一个圣，对啊，这是没什么，真相是就是没有啥，没事。哦哦哦哦哦，但是我的应该是最快结束。对对，OK，还有2个星期就结束了。学期快结束了。对，SD 应该还有一个，这个一个比较大的。我在想，有肯定有，就是买一个或2个，我觉得比较大一点会比较好。你哪个去买？做一个大的，也没有时间跟我说完。那你待到那吃完，那你就待到那吃完。什么？待到那记得吃晚一点，再晚会晚过那个一圈。Okay, let's start. I think we will go into the last chapter for exam purpose, which is accountability and separability. Separability. Um, Later, we will introduce another term called separable. Okay, it's a different separability here, so be aware. There's a separable, and there's some separability. Okay, it's a different thing. After this chapter, we will, if time permits, then we will do a little bit more of complete phase. And I think we'll do master presentation in class. Plan to do it on the week 15. I need to check with these master students again. Okay, so let's start with accountability. Okay, we say that a topological space
X is said to have a countable basis at X. Okay, so what it means here. So last time I talked about basis, right? But now we want to count the basis. Okay, so how to count the basis? If there exists a countable collection B of open neighborhood. So basically, we just count these open neighborhood, okay, of X, such that for every open neighborhood X contain at least one of the element of B. Okay, so how we write into a mathematical form? So there exists a countable set script B. Okay, so these are the open set such that they contain X, and then for every other open neighborhood, let's say V X, you can find something from script B here such that B is inside. So meaning if you go to any point, okay, look at any open neighborhood here, there's a collection of set, okay, such that some of the element from this set here is contained in these V. And you just need countably many of them to do it. Then we will say there's a countable basis. Okay, so from this definition, what's the example you can think of? What space got countable set? So countable, right? You immediately think countable is bijective with what? Natural number, right? Okay. And then how do you use natural number to build open neighborhood? Okay, one of them is to use open ball. Okay, 1 over n. Okay, so for example, we say that R has a countable basis at x equals 0. Okay, so can you come up with script B or not using n which contains 0? You come up with some open set, countable open set. Any idea? I think Seng want to try. Sorry? Negative 1 over n to 1 over n. Okay, so if I give you any open interval that contains 0. Okay, so for example, okay, if I gave you let's say negative 1.5, and then let's say 0.1. Okay, can you find some guy in this set such that is a subset of this open interval? You know what n will work? 10. 10? Does 10 work? So 1 over 10 over 10 here, which is negative 0.1 to 0. Okay. Okay, so why you can do this? Why you can do this? What property makes you can do this? Can find this n here? What property? Archimedean property. Okay. All right. Okay. So this is just an example. Okay. So try and prove that this is a countable basis. Okay. use the assignment question that you know how open interval in R looks like. Okay, so a topological space that has countable bases at every point. Okay, so you can imagine that R has a countable basis at every point. You use a similar ball but shift it to every point, any point. Then we'll say that this topological space satisfied the first countable axiom. First countability axiom. Okay, or we say that it is first countable. Okay, so let's give some example. So actually we can generalize the idea of R to general metric space. So actually every metric space is first countable. Okay, meaning at every point they contain a countable basis. Okay, so what's the countable basis you're looking for here? Exactly consider script B to be the ball with radius 1 over m. Okay. Okay. The idea of real number can generalize to general metric space. Let's see. Let's give you another example, but this is a non-example. Okay, we can show that actually R with the co-finite topology is not first countable. Okay, so meaning at some point you cannot have countable bases. Okay, it's not enough to have countable bases at some point. Okay, so still remember what's a co-finite topology means? Co means what? Complement. Okay, a set is open if the complement is finite. Okay? And then you need to throw in the empty set and the whole space. Okay, other than this space to be open, you need to throw in the whole space. Because complement of empty is what? It's everything, right? But your R is infinite. It's not finite. So it's not open, meh? Cannot be, right? I want it to be open. So I need to manually add the empty set in. Okay. Okay. So let's see how we do this. Okay, let's see what's the technique here. Okay, suppose by contradiction, okay, to contrary that this space is first countable. Okay, this space is first countable. And if it is first countable, then we can find some script B. Okay, and then we can enumerate these countable bases. Okay. So let's unravel what this means. Okay, so let's unravel what this means. So well, for every non-zero y, okay, you look at R, take away this point here. So this is a complement of a finite set, right? So this is open in particular. Okay, but it is open set that contain 0. Okay, so we look around 0. Okay, look at around 0. This open set that contains the 0. But you have this countable basis property, right, at every point, in particular at the 0 point. So meaning what? So you will find some index such that 0 will live inside this BJY and then live inside this open set here, because you have a countable basis at every point, including 0. Okay, make sense so far? You have a basis element live inside an open set. So far, okay? Okay, we just write down what countable basis means here. Then we can look at this inclusion here. Okay, we can look at this bunch of inclusion here. Well, let's see. So this is what I want to do. So, but then not that 0, okay, staying in the intersection of let's see, let me write down first. Let's see if this is correct. So 0 will live inside the intersection of OBI. Is correct? Intersection of OBI. Let me think. Feel like this seems wrong, eh? Maybe the BI doesn't, one of the BI doesn't contain 0, then this intersection won't contain 0, right? Is this true or not? Okay, let me write down this statement. You need to decide whether this is true or false. True or false? Could it be a case that BI doesn't contain 0? Maybe some BI doesn't contain 0, right? Maybe, yeah, depends. If it doesn't contain 0, then the intersection won't contain 0. Okay, I think this is not good. Maybe this line we don't need it actually. How about this? I make the intersection smaller a bit. Okay. I just look at all the J. I think all the Y bar. All the Y not equal to 0, BJY. I think this one works. This one works, right? I just repeat this construction for a different Y. Okay. And then next thing I want to write down is actually this intersection, you only get 0. Is it true? Why? Hmm. The point here is what? You cannot contain more than 0.
It's in R minus Y. So BY does not contain Y.
Okay. Hey, about right already. About right. So I think we still need one more line to see it clearly. So we do it for all Y non-equal 0, right? So what? How to put this obviously? Eh, how to put this obviously? Let me see. So you got R, right? The whole line R. Then this is 0, right? Okay. And then for every BJY, you throw away Y. Correct. Throw away Y. Say again. Not true. After intersection, meaning we throw everything. Before intersection, we just throw Y, right? So for every BJY, I just throw Y only. But after all the intersection, you throw all the Y non-equal 0. Yeah. Okay. Yeah. Okay. Okay. So what we have shown is actually 0 equal to this thing here. Oh, but it's not enough. No wonder I need that thing. Is it enough or not? Let me think. Sorry. Wait. So let's see. We want to draw some contradiction here. So this will implies that this zero set here equal to this intersection. Okay. And then we can try to take away this set here, which is take away the intersection. And then this is by De Morgan's law, we get R take away BJY. Wait, so sorry. This is just Y not equal to. How big is this set? How big is this set here? How big is this set here? Uncountable. Okay, not good. I mean, R throw away some points uncountable. Okay, so this is not good. There's no contradiction here. We try to, okay, so let me tell you the strategy. The strategy is try to get some contradiction from cardinality. Okay, but this case here, we are counting uncountably many of them. So don't have contradiction on cardinality. But do we have contradiction in other way or not? Not really. Really or not really? Not really, right? Not really, because take away this really is just y. Then you sum all y not equal to 0, obviously is the same set. So it's not good here. Right, so just now I plan to put something inside here. Why it doesn't work just now? Let me think again. Yes. Yeah. B is depend on y, yeah. Which one? Which one? It's not the same. Yeah, sure, not the same B for all y, yeah. Maybe could repeat. Let me think. Which B? What do you mean? So okay, so let's repeat again. So for countable basis means what? If you give you an open set, okay, around this 0 point here, if I have a countable basis at 0, you can find an element from your countable basis, I guess, such that it contain 0 and then contain in the open set. Yeah. This one live in different script B. Oh yeah, exactly. Yeah, sure, definitely. Yes, definitely. Yes. So where's the problem? Let me think. So any problem here? So okay. So are you saying that we want to do it like this X here, and then, So this script B is different for every X, right? How about I put it here? How about I put it here? Yeah, so let's think about it. Okay, I think there's one point we missed just now, right? Because at every Y, BI you pick is from different script BU. X. Yes, I think this is quite important point. That's why we get confused here, I think. So how we relate this? Let's think. So let me think. I think this argument still work just now because since BJY contain is something take away Y already, so basically you take away all the Y. But what is this guy here? How do we come out with this countable thing? With countable basis with 0. Yes. Yes. So yeah, let me think. Yes, I think yes. So this is the thing from 0, I think. Does it make sense or not? Huh?
Because every BJY should remains in BI 0.
So this B0 should come from the script B for 0. This one comes from script B for 0.
This is because BJY is open at contain 0, so it should contain an element.
Let me think again. Yeah, definitely. So this part is using the countable basis from 0. Countable basis from 0. Does it make sense? So yeah. Yeah.
Which maybe
You mean this intersection or this?
this BI 0.
BI0. Do you mean this? Let me think.
We only know that each BJY contains some basis element in script B0, but why average?
Okay, so you mean that so this is another open set, right? So this open set you applied it to the countability of 0, then the contain something BI from script B0, and then yeah.
My claim is that
Mhm.
I think we're not going through every natural number, only some of them.
What do you mean?
我用中文说吧，就是它可能我只知道每个 BJY 里面包括了一些 BI，但不一定包括所有的 BI。
And then
所以你的这个 intersection from one to infinity，
可以变什么？
就觉得你这个 intersection from one to infinity，
不一定成立。
但是就算这个不成立的 proof 接下来是可以做的，因为就算你，因为它是一个 subset of countable this number is countable, so it should still countable. So your following this is still work. That's why I think this intersection from one to infinity thing is a bit problem.
I don't think there's a problem. OK， 先不要看这边先，先不要看后面先啊，我们先看看这个 subset inclusion 成立吗？If this BI is coming from the B0, right, script B0, all of them should contain 0. So this set is subset of this one. Okay, now we need to settle why this second subset inclusion is true. Why the second subset inclusion is true? So for all bjy, right, they should have some bi0 sitting in the between 0 and this bjy. This is true for all bjy. Hmm? So think about it. So for every bjy, maybe there's some b0 ijy. Yeah. I don't know. So let's write down. Or for all bjy, there'll be something bijy. Depend on jy, so I call it ijy. Okay. So I take intersection on right hand side. I take intersection on left hand side. Then the subset. So okay. So if I put intersection here, sum over jy, not 0. Then here I do sum over j not equal to 0. Makes sense. This one makes sense or not first? If you have a subset, right? So I mean like you have a subset inclusion like this, okay? You got one bjy outside, one a inside. Okay, and then you look at all the intersection of this big thing and all the intersection of this small thing. The intersection of the small thing should live inside the intersection of the big thing. That's true or not? Let's look at two example of two 不要想这样远先 right? So let's say A in B, C in D. Is it true that A intersect C is in B intersect D? So if you are in A intersect C, right? You are in A and in C. Then if you are in A, then A is in B, so you are in B. But that point also in C, but C is in D, so C is in D. So your point is in D. So your point is in B and D. Okay. I mean, like, if you like, I drew another picture for you. Maybe A, B like that, B, C like that, and then B like this. And then C, C maybe like this. Right. Is it? Intersection. Thinking that okay. But here, maybe not this many. And maybe actually, yeah, maybe not this many. Because maybe some of the IJY can repeat. It a priori can repeat. But at most, the intersection you get is countable because there's a countable basis here. So you take even smaller intersection here. Even smaller intersection here. Okay, does it make sense? 懂我在讲什么吗？这边的可能性这边的可能性不管你 y 有多少多只有这么多个，因为它是 countable basis，你的选择就有这么多，不是你要选多少次，只是你选的东西就有这么多个。你选100次，它也只有10个东西给你选吧。Does it make sense? Okay. So everyone happy with this inclusion here? Is everyone happy? You got question? Question? Okay, no wonder I confused here. This BI is the 0, the countable basis for 0. Okay, so in this case here, we don't want to use this. We'll use the better one. This is actually equals to the countable intersection. Okay, why we say this is better? So here is the magic. So let's take away this countable thing. Okay, and then this will become the union of R. Take away these bi 0. Okay. But what is this? bi0 is an open set in core finite topology, right? Meaning this is complement of that open set, right? Meaning this set is finite. Okay. So this is in particular a countable union of finite set. So how large could this be? Countable union of finite set. How large could this be? Huh? It is countable or finite. Countable union of finite. It is countable. Okay. So this says what? But if this R take away 0 is countable, how about R? You just add one more point in. No? R is still countable, which is a contradiction. Okay, so I want you to remember this cardinality trick. Okay. All right. So far, okay, everyone, okay? Yeah, so the key point just now we messed up was we have countable bases at every point S. Okay, and then we try to reduce to countable bases at a single point. Okay. Any question? Any more question? Yeah. Yeah. Uh, just open neighborhood is enough. Open neighborhood. Yes. Uh-huh. 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 Yeah. Yeah, yeah, yeah. Yeah. Why do I need to? No, I just pick a specific open set that contains 0. What's the issue here? What's the issue here? Yeah. And then my contradiction, yeah. My contradiction is suppose it is first countable, yeah. And then so at every point you have a countable basis. Okay. And then I try to draw contradiction from here. Yeah. Never mind. Yeah, you try think again. If you have a question, you can come back. Why do I need this BJY? I think this BJY, I think it's better to put Y somewhere else, not BJY. Because usually when we put BJY,
it's just that everything you use is from B zero. Your B. I feel like the BJY plays the role in equating them.
yeah, this part, right? This
So far, will
Yeah, this part, right? This part. This part here.
Yeah, yeah, 但是就蛮多余的，因为 actually every r minus one intersection is just a zero.
Every what?
Every r minus one intersection is already zero. So actually you can just skip the matrixing.
Let me think. Oh, oh yeah, yeah, sure, definitely. Then we don't need this y anymore. Actually, these bjy are coming from this set here. Yeah, yeah, yeah. Yeah, so bjy here just picking from bi0 here. Yeah, 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 makes sense. Yeah, yeah. Oh, yeah. So okay, so in that case, then maybe we make some remark here. So this jy here is coming from script 0, script b0. Yep. Yeah, yeah, makes sense. Yeah. Because it's the open set on 0, right? So I go, because at 0 is countable basis, so I go to the script b0 and find this bj1. And then this will sum over all the y not 0. Okay. Okay. Any more? Any more? Okay. Okay, good. Yeah. Okay. So next part, what's the usefulness of this first countable set here? So with this first countable space, we could use convergent sequences, okay, to detect limit points of set, or we could use it to check continuity. Okay, so let's give a theorem here. So if you have subset, okay, of a topological space, if there is a sequence of points of A converging to X, then X is in A bar. Okay, I think this one is quite obvious from what we did before, but the converse will hold as well. Okay, so meaning if X is countable, okay, then if X is in A bar, then there will be a sequence converge to it. You can find a sequence of points and converge to these limit point. B, if F is continuous, then for every convergence sequence, xn to x in X, the sequence of fxn converges to fx. Okay, so maybe for you, right, how to discern the continuity between these two statements? What's the first continuity? What's the second continuity here? You might think that, hey, I thought this is definition. Is this a definition of continuity or not? Not in this class. So we define the continuity in this class for topological space using the open set. So in metric space, these two are equivalent. Okay, now you will know why this is equivalent, because metric space is first countable. Okay. So if you ever met your junior, you tell them you are just studying first countable space. Okay. So what is always true is if you have open set continuity, you always have this convergence sequence property. But the converse is true only if X is first countable. Okay or not? So if you want to use a convergence sequence to check to check whether the F is open set continuity or not, you only can do it in the you can always do it in the first countable set. Because there's an assignment question telling you that the converse is false, right? Which assignment? Yeah. In the assignment, right? You show that it's continuous, but if you go and look for, you can look for some convergence sequence such that FSN doesn't converge. Okay. By the way, I still own you 2 assignment, right? Maybe I'll very quick. I'll own you the 3rd one already. Hopefully, I can reduce my debt by this week. Because I was previously busy with exam, so I already finished with the exam setting. When times come, I'll let you know what you need to prepare. Yeah. Okay. Soon I will return you the assignment. Assignment 5, huh? Okay. So the converse is not true, if you can go back and check your assignment 5. Okay, let's prove this. Yeah, let's prove this. This statement here, very quick. Okay, so let's do A as a warm up to remind you the definition. If X is in A bar, if there's a sequence of point of A that converge to X, what does it mean here? Converging means what? In a topological sense. Suppose converge in epsilon delta, you start with epsilon, right? Converge in topological space, you start with open set. Okay, you replace epsilon with open set. So you take any open U containing X, there exists an N such that for little n greater than n, Xn will live in U. Okay. So I mean, there's a theorem before saying that if this happen, the sequence of A converging to X. So I write down the term here. So more importantly, for every n greater than n, Xn actually live inside A. Let me see. Yeah, because sequence of A. Yeah, okay. Again, that these two together will implies that X is in A bar. From a theorem before. Which theorem? Anyone can recall what theorem is this? If you have these two conditions, you can tell things about A bar.
Absolutely. If I can only use every open set with you containing X.
Intercept A, huh? Yeah, so why I write down this part here, because Xn in A means intercept A. Okay. Good, very good. Okay, so when I say this by theorem, how do you find? 所以老师没有跟我讲哪一个 theorem 号码。不是 the point I want to tell you is not about which number you need to find. It's about what is the information you have. information you have will help you to find which theorem you need. For example, I want to show x in a bar, right? I'm teaching you a technique. So if you want to achieve this, go and look for theorem that involve a bar. Okay. And then what's the condition here? The sufficient condition. They've got open set of. So you go try and find some theorem that relate open set to this a bar. And then there's what Eric read out. Can you read out again, Eric? Okay, intersects A. So that's why I put down this line here, because the open neighborhood here contain xn, right? Want to intersect A. So who is the intersection? Xn itself is the intersection. Okay. So how about the other direction? Okay, let's do the other direction. So the other direction says what? If you live in A bar, I want to find a sequence. Okay. So let's write this down. So suppose x is in A bar, okay? And then we want to construct a sequence. And suppose x is first countable. Okay, so you got countable, you got a point. Countable work for a point. So try and use countability on this point. Okay, try to use countability on this point. Okay, there's nothing extra you want to do. So just look at a countable basis at this point you want to discuss. Okay, then the goal here is what? Construct a sequence. So the goal here is construct a sequence Sn of points of A converging to X. Okay, so how to construct Sn now? How to construct Sn? Sn need infinitely many things, right? Infinitely many things. But you got natural infinitely many things here. Huh? Yeah. Choose X from each basis. Okay. If you choose X from each basis, right? How do you make sure it converge? How do you make sure it get very close to X in the end? Correct or not? You need to choose such a way that later it will converge. Converge means what? Just now we write down the convergence, right? Okay. So if you just randomly pick from BI, right? Maybe the point is quite scattered around. Okay? But you need to make sure this such that for all little n greater than some n. Okay? All the term will stay inside. Okay? I claim that there's one way to do it. Where there's one way to do it. You want to live inside some open set for all n. Okay, so there's one way to do it. So we define xn such that for all n in n, xn will live inside the intersection of finite intersection of b. Okay, and xn is not x. Okay. Okay, then now we need to check the property. Okay, so let's check the property. So for every open U containing X, okay, then by the first countability property, at x. Okay, we can find index n such that Dn live inside U. Okay, but for but moreover for any p that greater equals to n, if I look at the intersection, okay, from I equals to 1 to p of bi, this will definitely live in Bn. Yeah. Sorry. Intersection with A. Okay, before that, okay. So okay, right. So what's the problem here? What do you want? You mean intersect like this? Huh? Oh, what's the issue here? Do you want xn living? Okay, wait, let me see. Okay, so let's see is our Sn in A or not. So you want to settle whether this n A is in A. Mm-hmm. Mm-hmm, mm-hmm. Definitely. Yeah, so why this Sn is in A? Yeah.
It's because X is in
X live in A bar.
X lives in a bar, so
Mhm.
that this living intersection is a finite intersection of open set, so it is open, and this open set should intersect the A at some point other than X.
Ah, okay, makes sense. Okay, good. So yes. So why it works, huh? So let me put here why it works here. Okay. Okay, maybe I don't want to write intersect with A, but I will write xn is in A. Okay. So why it works? Okay. So whenever we define these things, right, we need to show that why it works. So let's put this together first. So it works because finite intersection is an open neighborhood of X. Okay. So repeat the A bar condition just now. Okay. So A bar condition says what? For every neighborhood of X, okay, you must intersect A non-trivially. Is it? Is that what Eric read out just now? Okay. So there's a non-empty intersection with A. Okay. So you can pick some point from A. Can you make sure that this xn is not x? Huh? Cannot.
Because A bar is only not limited point by own also something.
It could be a what?
Yeah.
Oh, okay, okay. So can we make sure this? Do we need to make sure xn not x? No need, right? Yes, that's right. That's right. Okay, so I think I write the wrong one with the previous. I think I need this condition instead of xn not equal to x. In fact, you might not know whether Sn is can be not equal to x or not. You don't know whether this intersection point here is x or some other point. What you need to make sure is the following here, this part here. Okay, as long as converge. Could be eventually converge, eventually x, or something like that. Okay. Any question? Huh? I don't know. 80% pay meaning 80% explanation. Okay.
But in order to make the image of
Okay, any question about this proof? Yeah. Okay. No question? Any question? So convergent here doesn't need xn not equals to x, but you need xn in A because we want the sequence to be in A. And then convergent here just guaranteed by the intersection. Intersection property. Okay, because whenever you take intersection, it gets smaller and smaller. Again, like this small intersection here will live inside chosen at the end. When your P here increase, the intersection here getting smaller, smaller, and smaller. So that the xn you pick will live inside the SP you pick will live inside the B. Okay. Okay. In that case, let's break until 1111. Hmm? Hmm. Yeah. 什么？啊，没有问题啊。只要你那个，I mean，如果你的 X 活在 A 里面，呀，看一下刚才那个点，呀，如果你的 X 活在 A 里面，你有可能会选到 XN，你 XN 可能会选到 X，但是管你怎么选啊，我一定有这个 convergent 的 condition，是因为我是从 intersection 里面把它选出来。如果你的 X 不在 A 里面，那你就不会选到它。但是我还是有 convergent。convergent 是从intersection 来的，然后每个 intersection 是 finite 的，所以它是一个 open set。 ？BI 是刚才那个 countable basis 来的。
哦，X，
嗯哼，啊，
所以为什么我不会选有个 X？
哪一个
为什么不会选 X？如果你拿 X，你可以
？X 可能不会活在 A 里面。X 如果活在 A 里面，你再来选 X 就好了。X 可能不活在 A 里面。
对啊，他只是说 X 活在 A8里面，X 不一定活
它的重点是这个 XN 在 A 里面，你如果 X 在 A 里面可能会遇到它，也可能不会遇到它，但是重点是它是在这个，他们是活在这个 intersection 里面，然后我就可以有这个 convergent 的 property 了。
OK，
它 convergent property 是从 intersection 来的。Yeah，
让我看一下你的分析。
给我20%的功夫，好不好？
跟你相谈。
我操！所以这个 basis 会小过所有 neighborhood 的其中一个 basis。
嗯，
周五的时间来看电影吧。
几点啊？
几点？
到几点
9点半吧。
？9点半。
呃，
看一下。
看一下是看电影看一下还是
不确定，因为我有
没有
FYP 的。
因为我没有来，对
因为我们都有来。
definition 没有看
哦
到，
，2点没来。
他身体也不舒服。
讲的很好，那我来看电影。
啊？怎么嘞？你们要留位置来的？
我们有点空。
你要比那太恐怖了。Half of the committee must
哎，叫他们去。
蛮凶啊，控制一下。
再跟你们讲，再跟你们讲，再跟你们讲。他是有钱的还是不要钱的？
用钱啊，
不用钱的。
对
啊，
看戏吧，看那个数学家，看那个
我知道 John Nash， 啊我看过啊，
所以我们这个
啊，
所以你第一个 xn 是从随便一个 v 拿了，还是你从 v 拿？
可以有顺序，你随便乱来也可以，但是 as long as 你是来
越来越小。
呀，反正它 intersection 过后会越来越小。我这个顺序是跟之前的顺序哦，你要跳也是可以的，但是你跳也是等于这样 relabel 啊，所以就
v 一哪一个，v 二哪一个？哦，没有 v 哪一个，v 二
然后第一个
v
V 二的 intersection。
第二 v 三哪一个？
对，一点一点，
不舒服。我早上一些头痛，
你又痛啊？
头的。en 是在这个里面对吧？是。所以这个肯定是 subset of 它，因为它在里面。OK， 接下来我不知道他们做这个 first countability axiom 的想法是什么啊？maybe 他们是反着正，然后突然发现到我要这个东西，他就讲一句，还是有什么 concept 在里面？
我不懂哎，但是至少我来说是，他可能我不知道他是，我不懂，我不知道他们怎样找到，
就讲这个，
但是这个性质找出来是蛮 obvious 啦。 但是这个性质会 imply 这些东西，我是不知道他们怎么会忽然间觉得说是这些东西有了过后，这些东西才有啊。
先讲这个性质上。
I mean 这个东西很 obvious，因为那个 ball of radius E over n 是 countable 的嘛。
你讲 set out 这个 open 的是 countable。
对啊，这个很 obvious 嘛。但是至于说为什么我要把这个特性 link 到那些东西，蛮神奇的。或者可能他们发现到，哎，其实他选的 sequence 就是被这些 countable basis 包在一起，然后包在一起的性质可能就是 intersection 吧。因为它越来越近嘛。OK，你想象那个 epsilon delta 的话，它是越来越近，越来越近，越来越近嘛。然后你就可以想象 contain 它们的 interval 就越来越短，越来越短，越来越短。但是你怎样解释这样越来越短呢？哎，一次跟它 intersect 下来哦。
但是做还要 countable。
哦，对，这个是一个问题，就是来，因为我们的那个 convergence 是用 n 来控制嘛，
哦
对吗？
不能。
我们用 n 来控制嘛，then first countable 就够了咯，就够了。Yeah。
要找 countable basis 其实蛮难的吧？
basis。看呀，可能哦，有时候 look 呀，random topological space 可能有点难吧。
哎，我们在 R 里面就是这个 set 啊 open 的嘛，
因为它是 open set 呀。
你也可以一边想，对你拿么 open level 都好，你可以把它变小。
嗯哼，嗯哼。
但是如果我的 open level 是connected 的，也是可以哦，没有问题。
变紧啊，我只要保证我在零附近可以保到就。Let's start to. Okay. All right. So what have we observed here? Okay, so the idea that Eric mentioned just now is this line. Okay, you have to remember S is in A bar if only every open set U containing X intersect A. Okay, it says intersect A. It doesn't say X have to be in A. 不用. Okay, X may not be in A. This intersection might be some other point than X. Could be X also. Could be some other point than X. I hope you still remember the exam question. Could be X, could be outside X also. I'm sorry, in A or outside A. So from what we have seen just now, the convergent you see in MA is really just the intersection of open. Because when your epsilon get really small, right, you should think of it, the 2-point live in the interval that getting smaller, smaller, and smaller and smaller. Okay, so how do you describe this epsilon getting smaller and smaller? And use intersection. So you get all the intersection. So it gets small. Okay. Okay, wait. Okay. Okay, so we need to prove the continuity part. Let's do the continuity part. Okay, so let's do warm up first also. Let's do the first direction. So assume that F is continuous, okay, in the open set sense. Then we want to prove this statement here. So let's assume F is continuous. Okay, and then we need to show for every convergent xn to x, right? So let's take the convergent sequence xn to x in x. Okay, if I want to show that the sequence fxn converge to Sn means what? for every open neighborhood of fx, okay, you want to show that there exists a large n such that fsn with n small n greater or equal to large n live inside the neighborhood. Okay, so very clear what we need to do, but can we do it or not? Okay. So now you see this is an open neighborhood in the codomain. Okay, you have continuity. Continuity will bring your open set in your codomain to a open set in the domain. Okay. So then F inverse of this open neighborhood V, right? We'll call it V, is an open neighborhood of X. Okay. And so what? So what I want to write here is there is an n such that for n greater or equals to n, this implies that xn will live inside the F. Why? Why this line is true? Who give you this existence here? There's one condition we haven't used yet. Yes. So we have xn converge to x here. So xn converge to x means what? You build any neighborhood around x. So this is in particular a specific neighborhood around x. There will be a n. Okay, so this n here should depend on f inverse v here. Okay. So I have a open neighborhood of x, and then there's an n such that this is true. But then this implies what? This is the same n you need to show that fxn is living in V, set theory. Okay, so here. So we just use assumption. Okay. So this course is really about set theory. Hey, before that, just now, our student council asked me to make a promotion for their movie night. So there's a Friday movie night. What time? 7 to 10. Got popcorn or not? Okay, bring your own popcorn. So there's a movie night at where library? A3 104. Okay. It's about a beautiful mind. So it's featuring a mathematician called John Nash, right? Nash equilibrium. Okay, Nash equilibrium. So this mathematician didn't get Nobel Prize, didn't get few medals. No, he didn't get few medals, but he get a Nobel Prize in economics. Yeah. So you can see how he go crazy in the movie. It's free. Okay, it's free. No need to pay. Chinese subtitle. Wow. Okay. Yeah, for everyone. So you could ask your friend. Non-MAT also can go. Yeah, you can bring your friend. Okay. Bring your 室友 go. Okay. Yeah. Who have to contact? Do they need to contact you? Send the teams. Send in my GT team. Oh, okay. You can send into our team or your mathematics family also good. Yeah, mathematics family. Yeah. 对呀、如果他们要去的话，要联络你们是吧 ？Register link. Link is in the mathematics family. Okay, you can post in the GT group also. Okay. Okay, so how about the other direction? Again, the other direction needs some work. So you want to show that if x is countable, okay, and then you know that every convergence sequence converges for fxn as well. Then f is continuous in the open set. Okay, so how do you link open set to sequence? So you need to think about how to link sequence back to open set. How to link sequence back to open set. We just did it. Okay. So we could link sequence to open set here. I mean closed set or open set. Okay. So that's why this theorem is AB. Okay, we're gonna use A later. Okay, if X is countable, then we can go from closed set to sequence. Okay, let's see how we use this. Okay, so let's write down what we have. Okay, so in mathematics, if you don't ever want to do pure maths again, never mind. But what you want to get out from this pure maths course is write down your assumption. 你有什么假设？你有什么东西可以用 and then start from there. Okay, start from there and then cook out. And then what other assumption you need? Can I add it in or not? Can I manually add it in? Or is it implied already? Mathematics is like that. This condition is not implied. Okay, throw into a theorem condition. So that's why sometimes you will see, theorem, assume this, assume this, assume this, assume. Why? Because we want this to be true, only then we can get the result. Okay or not? Why we must throw the condition in? If not, maybe got contradiction. Okay, so this is a way of thinking. This is a mindset. Okay, this is a mindset that we want our student to have it. Even though you don't do pure maths, in a reality, it's like that. Hey, 你讲我没有做事啊？你讲我没有什么？我跟你讲我有做事哦，我给你这个 point 咯 example 咯 counter example 咯。不然他讲我没有做事哦，他不要请我薪水怎么办？我一定要 argue 给他听吗？我有做事吗？对，这个不是做事咩？你不明白这个咩？这个气到不好咩？你不明白，我不是教你哦。你能的话，你自己去考一张出来哦，对吗？你能教学生，你去教看你能教多好，是不是？我 evaluation 我有证明我 example 嘛，对不对？不是这样讲。我不可以跟他吵架，我给他 example， 是不是？就这样讲。Okay, use mathematics to argue. Okay, so assume X is first countable. So we write down all the conditions first. And we know that fxn will converge to fx for all xn converge to x. Next, okay? This is the only thing we know. Then we want to show that f is continuous. So last time we have a few equivalent definition on continuity, right? But since A is about closure, then we will show that the closure property on continuity, which is to show that f a bar is in f of a bar is sitting inside the closure of fa. Okay, this is the non-obvious one, right? Last time someone said that this is non-obvious. But today we use this to show it is continuous. Okay. So how do we show this? Huh? There is a contradiction. I mean, no contradiction. There's a counterexample. And although it's continuous, it might not be equal. Because your okay, so one way to think about it is maybe your closure will add in more thing that you need. One way to think about it. I don't think so. I don't think so. Yeah, I think it's a subset, right? Last time. I think I pretty sure I remember it's a subset. Okay. So let's see how we show this. So you need to check for every A, look at the element in A bar, apply F. Is it live inside the closure of FA or not? Then you just unravel all the definition. Okay, so let's take X in A bar. Okay, then what A tells you by A, there exists a sequence from A converge to X. Just now we proved, right? Just now we proved using the intersection of BI. Okay, so you see from A bar cook out Xn already. Just now you look at the statement. Sequence or how to imply open. So if you live inside closure, then you will cook out a sequence already. Just now what we proved in taking the intersection of BI. Okay, using the first countability. So you got the sequence in A already, right? Converge to X. But your assumption says what? For this kind of sequence, you apply F, it also converge. Okay, so then by assumption, Fxn will converge to Fx. Okay. But now, what does this mean? This just means that Fxn actually live inside Fa. No, not this means, because Sn repeat from A, right? Okay, so Fxn live inside Fa. So, do you need to use lemma again? Or is it enough already? So by previous lemma, Fx will live inside Fa bar. Okay, so previous lemma, see again. So if there's a sequence converge to X, so here you got Fa, right? A sequence of Fa converge to Fx, right? Then Fx will live inside Fa, Fa and then bar. Okay, because this is A bar, right? Okay, so we replace A with Fa, so this A becomes Fa bar. Okay. Hence, Fa bar live inside the closure of Fa. Okay. Does it make sense? Okay. So hopefully, out of this class, I could convince you that you just need to put assumption, and then your solution will drop out. Okay. Yeah. Obviously, in reality, maybe there's some more step, but this is the backbone. Okay, this is the 框架. Okay. 马来文是 rangka 框架. Okay, 框架 is very important. Okay, next. So last time we know that Hausdorff space will give you the unique limit property, right? But if I know that X is first countable plus every convergence sequence, every convergence sequence has a unique limit. Quantifier is very important. Peter complained to me, the MA people didn't put quantifier. Don't know what they assume, don't know what they prove. Then X is Hausdorff. Okay, so this is the other way around. If I know that my space has unique limit, okay, plus first countable, only I get Hausdorff. Okay. Previously, if you are Hausdorff, then you already have unique limit. But how to go the other way around? There's only one thing you need to add it in. It's first countable. Then you are Hausdorff already. Okay, let's try and show this. Again, write down what you know first. So suppose X is first countable. Okay, instead we will use proof by contradiction. No, proof by contrapositive. So meaning if X is not Hausdorff, then there exists a convergent sequence with distinct limit. Okay. All right. So since it is not Hausdorff, right? Oh. Okay. So it's first countable, and then it's not Hausdorff. Then there will exist 2 points, A not equals to B, such that every open neighborhood of A will intersect every neighborhood of B. Okay, because Hausdorffness just require existence of two neighborhoods that avoid each other, right? Okay, so if you cannot find the existence, then every neighborhood must intersect. So then we just take the countable basis on A and B now, okay? Because our space is first countable, right? So let's take countable basis at A and B. What do you want to cook up? A convergent sequence that converge to both. Zhao Shen, want to try again? Find a convergent sequence. Just now I asked you find another one. Try and find this one. That converge to both. Okay, what kind of intersection? So now we construct Sn. How to pick from what intersection you want to pick. Wait. Intersect O? Okay, let's say S1. Let's tell me how to pick S1 first. Okay. S2 leh? N2 intersect N2. And then? Okay. Enough or not? 好像重复了3个小时的情节。Enough or not? Not enough. What more you can do? Huh? XI, okay. I mean, this pattern, I know what is XI already. But the question is this enough or not? Can you make sure the convergence for every open neighborhood around AB, and then you can have the eventually Xn stay inside the neighborhood? No. Yes. You think yes? You think yes? I think we need more. We need more. We need even smaller. So let's do even more. Instead of this, we'll intersect with the previous open neighborhood as well. Intersect with the previous open neighborhood as well. Later, we will try and show, and then you will see that this condition quite important. So instead, we will do Sn living inside intersection of I equals to 1 to n of Ni intersect. Okay, so let's see this word or not. Is this small enough? So let's take, for example, let's check around A first. If it is in A, then there exists a countable neighborhood around A is nj, right? So there's a nj living inside U such that for all k in J, okay, xk will live inside intersection of I to k of ni mi here. Okay, this guy in turn live inside nj, and then nj live inside U. Right, so you can do that similarly for B. So meaning what? The intersection here, ni and mj here, just for you to contain in the neighborhood around A or B. But this intersection here, this large intersection here, is make sure that you stay inside your nj or mj eventually. Okay, so you need two intersections. OK 啊，可以吗？到这可以记得吗？这个大 intersection 蛮重要的。OK。Okay, so similarly for B. Okay, so far okay or not? So far so good. Okay. Okay, if okay, then we'll move on to second countability, which is second countability. So second countability means if a space X has a countable basis for the entire topology, okay, then X is said is second countable. Okay, can you see that second countable stronger than first countable? First countable just that every point got countable basis. This one, lump sum, you only got countable basis for topology. 全部的basis 只要从这个 set 里面找就好。Just now every point, right? If your point got uncountably many, then all of these will be uncountable union of countable basis. But here, all together you only have countable. Okay, even less. Okay. Because this is so strong, so strong until maybe not every metric space have this property. Yeah, not every metric space. The example I gave you just now, if you are countable basis at every point, but your point got uncountably many, right? If you add all them out, then uncountable. Okay, it's not countable. Okay, so not even metric space can handle this property here. So let's see. So for example, surprisingly, R is still second countable. If you think about just now the open ball, you add them out, or surely uncountable. Okay, but surprisingly, you still can find countable bases here. What do you think? This example actually you see before also in the assignment. Just this is a different way to interpret it. Sorry? A to B, yeah, A to B. So what kind of AB here? Countable, right? Countable, always countable. What you need to think about it? Rational or natural number, right? So last time we showed that we can replace the basis of R to a rational endpoint. I asked you to show in the assignment, right? Okay, so it has a actually countable basis. Just that you need to consider your basis with all the open interval. AB with rational endpoint. Okay. And similarly, Rn is second countable also. Okay, so you can try and think about how you cook up this rational property here. I think you use rational ball, is it? Yeah, I can try and think about it. Why Rn is second countable? Sorry? Rational rectangle. How do you think about rational rectangle? Ah, okay. Okay, if you want to talk about that case, with rational vertices. Okay. I think ball you also can take rational ball, right? Rational ball works. Rational ball with rational radius, I mean. Okay. Right. So maybe one more interesting thing is infinite product of R is second countable too. Can you think of a countable example here? Sorry. Can you think of countable basis example here? Here we consider product topology. Still remember product topology means what? Finitely many is a UI, which is not the whole space R, just finitely many. So you just need to control this finitely many coordinate here. Okay, so you just consider the product of UN, where UN is what we have for our R. We just consider open interval with rational points. But for every such product, right, there are only finitely many of them. Okay, so it's still countable. But all the rest of UI should be the whole space R. Okay, this is what we call the product topology. Okay, if box topology, then you could have random open interval cross together. Okay. Okay. Okay, next. So we'll say that a topological property is hereditary. Okay, meaning if S has the property, implies that every subspace of it has the property. All subspaces. Okay, last time we see that compactness is not hereditary, right? Because if you look at the closed interval 0, 1 is compact, but open interval 0, 1 is not compact. And another thing is about productive. Okay, how is it productive here? It means that if you are compact, okay, then any product of compact space have to be compact. We have shown it for finitely many already, but later we will show it for infinitely many, which is called the Tikhonov theorem. Okay, so productive means it has to be true for arbitrary product. Okay, any finite infinite. Okay, so what we know now is theorem. Both first countability axiom and second countability axiom are hereditary. Okay, so if you have countable bases in X, how do you reduce to subspace? How do you reduce to subspace? Just take intersection. Okay, just take intersection. Just take intersection. Okay. then it's also countable. But they are not quite productive. They are not quite productive. But it is true for countable product. Okay. So the subspace kind of argument, right, is true for countable product only. Okay, so meaning countable product of first or second countable space is again first or second countable. Okay. Okay. Okay, because countable product of countable thing is still countable. That's it. Okay, for this proof. Okay, makes sense. Maybe this statement is interesting. If you can think of why is it not productive? Can you find not just countable, maybe need to be uncountable product. There is not maybe uncountable product of first countable space is not first countable. But just now I show you it is right for the Rn case. Can you come up with other uncountable product of such that it's not first countable anymore? For example, you can think of the infinite product of R using box topology. Okay, and then see whether it's first countable or not. Show that it's not first countable. Okay, for box topology. Okay, this proof I just leave it to you. It's just a subspace proof. Okay. So next, I think did we define dense in assignment already? Have we defined dense in assignment for the no. I'm pretty sure this assignment also got the Cantor setting. Okay, so again, I remind you what is dense. A subset is dense in X if A bar is X. So you add in all the limit point, you get the whole space. For example, Q is dense in R. Okay, because precisely we add in all the limit of Cauchy sequence, okay, of rational number to build R. Okay, so here's the theorem. Suppose that X is second countable, then let me introduce a new word for you. This is just a property, but we call it a name because it could exist at its own right. So we call it a name. So it's called a Lindelof space. Okay, so what does it mean here? So if you are second countable, then for every open covering of X, it contains a countable subcollection that covering X. Actually, this makes sense, right? Because if you are second countable, you have a countable basis. So meaning countably many things can cover X already. So but the point here is every open covering of X you can reduce to a countable subcollection. Is this obvious? You have countable bases can cover, right? But this one is an open cover. Then you need to somehow drop your open covering here to your countable bases. Just need to cover your countable bases. So you need a countable subcollection to cover them. Okay. Second, but why we give this the name? Because this could happen at its own rights, meaning maybe it's Lindelof but not second countable. Okay. Second is separable. Okay, separable means if it is second countable, then there exists a countable subset which is dense. less than in X. Actually, I'm not sure why this condition calls separable. I don't know. I don't know who gets separated here. Huh? So you see, the so the countability for bases, right, reduced to a countable sub-collection of covering, and then reduced to a countable subset of X. I think this one quite strong. You just need to pick countable element, okay, from X, a subset, countably many elements from X, so that you can build back your X just using limit point. Quite strong at this one. Okay, I think actually this proof is not too far. Should we do it quickly? Let's do it quickly. So you really just start with a countable basis in X. Okay, this is the only thing you had. You cannot run away from this assumption here. Okay, then for first one, you got a covering, right? So just let A be a open covering of X. Okay, so since you can write X as a union of Bn here, then you just choose An such that An will contain Bn. Okay, so that your X will be written as a union of Bn, which is a union of A. Okay, how about the other direction? How do you cook out the countable subset? Well, you know there's a countable many Bn here. So you just choose Xn in Bn. Okay. Yeah. So where Bn is non-empty. Okay, because maybe you can throw empty set into it. But we don't care here. So what's the countable set here? We claim that this Xn actually is dense. Why is it dense? Why is it dense? To show dense, what do you need to show? You need to show that A bar equals to X. So the closure of this set here is the whole X. Well, A is already come from X. A bar can only come from X because X is the whole space already. The only thing you need to show that is every X is a limit point of A. Okay, so given any point of X, okay, we're going to show that it is a point in A bar. But to check every open neighborhood, right, you just need to check on the basis. Okay, but every basis element containing X, okay, must intersect this set A. Okay, so X belongs to A bar. Where must intersect A? Why? Why every basis element containing X need to intersect A? So to check on every neighborhood, you can reduce to check on basis. Okay, and then to check on why every basis that containing X will intersect A. Because the A contains at least one point from all the Bn. Okay, and then yeah, from all the bases. Because this A is constructed by choosing at least one element, okay, from all the Bn. And then all the basis element here should be some element here. Okay, so it will intersect with this set. Okay. Okay. So pretty strong condition on second countability here. Okay, we'll see you tomorrow. We have to get out here pretty quick. We are late.